Hello everybody and welcome back to another video by Funlearn Tutorials. Today's video is again another important topic to be discussed under complex numbers. Nonetheless, it is a little bit more detailed compared to the other videos that we have done and the other topics that we have covered. So in today's video, we'll be first talking about modulus and argument, and subsequently we'll be talking about something called the conjugate of a complex number. So let's first start with what we know. Now this video where we talk about the modulus and argument of a complex number, we'll be referring to two videos that we have already talked about in our past videos. So both the videos, I will be linking them down in the description box below. If you think you can have a look at it before we start with this video, we are always ready to do that. So the first video that I'll be talking about is, not long ago, if you remember, I had said that any complex number, so let's say I have a complex number z equal to a plus ib. So let's say I have this complex number z plus ib. Now this complex number can be represented not just as a complex number, but it can also have an alternative representation in terms of two-dimensional geometry or in terms of the graph paper, where we represent this complex number as the point a comma b, right? So we know that any complex number has a point form. So whenever we look at a complex number and when we look at points on the two-dimensional space, that is the graph paper, we can find a one-to-one correspondence between complex numbers and between points in a two-dimensional space. So I will be connecting, or I'll be referring to the video in the card section somewhere around here so that you can have a look at it. That is one video that we have already covered. The next topic that we have again already covered, what I'll be doing is I will be again connecting the related video here in the cards, and again I'll be linking them down in the description box below for you to refer to. But what we did is we learned any point in the two-dimensional space. So let's say any point, not necessarily this complex number, but I'm just using, since I've used the symbol over here. So any point on the two-dimensional space, any point on a piece of graph paper, can be represented by an alternative system called the polar coordinate system. So I would like to write that down over here. So it can be represented in the polar coordinate system, right? So what was the polar coordinate system? Now in the video that we had covered, we had considered a unit circle, but in general, if you do not consider a unit circle, what happens is you can refer to this point in the form r cos theta. So you can refer to the point as r cos theta, comma r sin theta, right? You can refer to the point as r cos theta, comma r sin theta, where r cos theta refers to the point a, or refers to the number a. So this refers to the number a and this refers to the number b. Now in the video that we had covered, we had considered a unit circle. What is the characteristic of a unit circle? For a unit circle, we have r equal to 1. So these portions are they all apparently disappeared. So these portions weren't there in the video that we had considered. So let me look at the blue highlighter. These portions were not there. So again, if I want to highlight, this portion was not there. We found out that any point in the two-dimensional space can be represented as cos theta, comma sin theta. But that is only true for a unit circle. If we take a general circle with not necessarily equal to r equal to 1 radius, that is, we take a general circle which may not have radius equal to 1 unit, I will have the representation in the form r cos theta, comma r sin theta. Now why am I talking about this? So let me just remove this portion first. So here r is not equal to 1. So let me just write that down. R is not equal to 1. That is what we need to remember here. But that does not explain why we considered these two. Now why we considered these two is we'll be combining the concept of these two. So what we'll be doing is a complex number, this video that we discovered, discussed, the first video that I talked about, this video enables us to convert any complex number to a point in two-dimensional space. It allows us to convert any complex number with a real part and an imaginary part. So any complex number into a point in the two-dimensional space. The second video allows us to convert any point in the two-dimensional space in this form, represented in this form: a comma b, x comma y, p comma q, m comma n. Any point represented in this form can be converted to the polar coordinate system in this form. So r cos theta, r sin theta. So now, if we combine these two videos, so we have a complex number. A plus ib. That complex number can be converted to a point in the two-dimensional space a comma b. That complex number can be converted to the two-dimensional space a comma b. Again by video 2. So this one was by video 1. This one was by video 2. This point in the two-dimensional space a comma b can be converted to r cos theta. So a becomes r cos theta and b becomes r sin theta. Now, so we are going from one place to the other. We are going from complex number to a point in space, and we are going from a point in space represented in the form a comma b to the form polar coordinate system r cos theta, r sin theta. So if we want to make a shortcut, what can we do? We can directly move from this point to this point. Can we not do that? Of course we can. So what we'll be doing is, we know that this portion, the first portion represents A. This portion represents A. This portion represents B. So r cos theta is A. R sin theta is B. So how can we write A plus IB? So Z becomes, so Z was initially A plus IB. Now instead of A, I'll be writing r cos theta. So I'll be writing r cos theta. So r cos theta plus I. We have I. And then in place of B, we'll be writing r sin theta. In place of B, we'll be writing r sin theta. There we go. We have another alternative form of representing a complex number. To make it look shorter, we can take r common. So we have cos theta. We have cos theta plus I sin theta. So Z, a complex number Z, which was initially represented as A plus IB, can be represented in the form r cos theta plus I sin theta. Now what do we need? Why do we need to consider this expression? Thing is, this form of expressing a complex number is actually very commonly used. It is a pretty commonly used expression. Now we know that in complex number, considering this representation, this part is called the real part and this part is called the imaginary part. So we have a name for this part and we have a name for, well, we have a name for this part and we have a name for this part. This part is the real part, this part is the imaginary part. But do we have separate names for r and theta? Do we have separate names for r and theta? Of course, we have separate names for r and we have a separate name for theta. So what are those names? Essentially, we define r as the modulus of a complex number. We define r as the modulus of a complex number. And what is theta? So theta, well, theta connects to something called the amplitude. Something called the amplitude or the argument of a complex number. So we now know what is the modulus of a complex number and what is the argument of a complex number. That is the definition of the modulus of a complex number and the amplitude of a complex number. So whenever we get one complex number given in this form, we can convert it to the form r cos theta plus I sin theta, and then this number r will be called the modulus of the complex number, and the number theta, the radian measured in radian, will be called the amplitude or argument of a complex number. So then, what is the conjugate of a complex number? Conjugate of a complex number is a pretty easy business. So what we do is, let's say I have a complex number z equal to a, or maybe I have already overused a plus ib, so let me use a different color. So let's say I have a complex number z equal to x plus iy. So we have a complex number z plus iy. Now what will its conjugate be? So what will its conjugate be? So let me write that down. Conjugate of z. We will be finding out conjugate of z. So conjugate of z is very easy. What we do is we write the real part. So we write the real part as it is, and we reverse the sign of the imaginary part. So we write x minus iy. Had this real part, so this is the conjugate of z. So we just reverse the direction, reverse the sign of the imaginary part. Again, consider another complex number. So let's say I have another complex number x minus iy. X minus iy. So what will be the conjugate of this complex number? The conjugate of this complex number will be x plus iy. The conjugate of this complex number will be x plus iy. So you can automatically derive or deduce from these two little problems that we did, that the conjugate of a complex number is can be written as, so essentially when we talk about one complex number, the conjugate of that complex number is the complex number itself. So this is the basic definition of conjugate, modulus and amplitude. Now these definitions, these concepts have different properties connected to them. So in subsequent videos we will be referring to the properties that these three definitions related to complex numbers have, and then we will look at certain examples so that we know that we have understood the concept. If you have liked this video, then please write them down in the comment section below if you want to say something. Also like the video, subscribe to my channel and share it if you want this video to be seen by your loved ones. And till then, happy learning!